Hello, folks. This is going to be a quick introduction to before, change, and after tables, part two. But this time, instead of using a formula like making a ham and cheese sandwich, this is going to be instead using chemical reactions and looking at balanced equations like we have done in the past. So with that, here's the example problem that's listed on the packet. You should be following along with your packet and actually answering the questions as we're going through this to make sure you understand how we're going to be getting each one of these components. I am going to walk through example problem number one, and then I'm going to give you some time to work through example problem number two on your own before just giving you the answer straight out. All right, so example problem number one. A mixture of 30 molecules of nitrogen and 60 molecules of hydrogen were combined together. And you'll notice that we already have a balanced equation of 1N2 plus 3H2 goes to 2NH3, which is ammonia. And you'll notice that we've got the before, change, and after table all set up. But I also want you to notice that we've got these two sections right here at the top that we didn't talk about last week, but I am going to talk about pretty substantially this week. So that way it gives you an idea of how to use those things as a tool. All right, so just filling in what we know already, according to what we've got, we have 30 molecules of the nitrogen. I'm going to put 30 right here, 30 molecules of nitrogen. And we've got 60 molecules of hydrogen. Now, since this reaction hasn't started yet, that means we have 0 molecules of NH3. All right, so we've now got the entire before section filled out for the BCA table. Where do we go from here? Now, a few people even ended up asking me how to go about filling out the rest of it, and I had said, well, what did you do for the previous problems, and to use a simulator. But the simulator doesn't go up to 30, and it doesn't go up to 60 for sure. So what do I do to try and figure out the rest of this? Which one of these two is actually going to run out first? Well, what we have to do is figure out, well, is the nitrogen going to run out first, or is the hydrogen going to run out first? And the way I'm going to do that is I'm going to look at the 30 molecules of N2, and I'm going to divide it by the coefficient of the balanced equation of 1, and that's where this little box comes in, and I'm going to get a number of 30. We're going to do the same thing with the 60 molecules of hydrogen, but notice that the balanced equation ends up having a coefficient of 3 in front of it, which gives me then a number of 20. Now, one of these two numbers, now that these are actually based off of the balanced equation, not just what the question was asking, we can actually use these to figure out which one is going to run out first. And based off of that, this 20 is smaller than the 30. So this is going to run out first. So that now means I'm going to use this number and use it for every single one of the substances. It becomes my magic number that becomes the most important portion of this BCA table, because the hydrogen is going to run out first. So how am I going to fill out the change row at this point? Well, I know that the hydrogen is going to run out first, and I'm going to be using, well, the mole equivalent of 20 of them. So 20 times 1 means that this is going to go down by negative 20. The hydrogen is going to be, well, 20 times 3. This is going to go down by negative 60. The products, on the other hand, is actually going to be increasing in the amount that's being made. So it's going to be 20 times 2, which is going to give me 40. And since it's being produced, instead of going away, it's actually being added. It's going to become a positive 40. So with all that, now I have the entire change row. And let me recap how I got that change row once again. I took the number of molecules of nitrogen and in the before section and divided it by the 1 from the balanced equation and got my 30. Then I took the 60 molecules of hydrogen, divided it by 3 and got 20. And then I'm going to start to compare the 30 and 20 to each other, and the 20 is the smaller number, so that's going to be the limiting reactant. It's going to be the one that runs out first. I'm then going to use that 20 to multiply by 1, to multiply by 3, and to multiply by 2. to give me the negative 20 molecules of nitrogen, which leaves me with only 10 molecules of nitrogen left after the reaction's finished. There's going to be 0 molecules of hydrogen because all 60 molecules of hydrogen are going to go away. And then for the ammonia is going to have 40 molecules of ammonia that's going to show up. So at this point, I can ask a bunch of different questions using this table, and we should be able to figure out what they all are. And I'm probably even going to ask more than are on a worksheet that's in front of you. So how much nitrogen gets used? Well, 20 molecules of nitrogen get used. How many moles of nitrogen will remain after the reaction? 10 molecules of nitrogen will remain after the reaction. How much of the hydrogen is going to be used? Well, all of it. All 60 molecules are going to get used. How much hydrogen remains? 0 molecules of hydrogen will remain. How much ammonia is going to get made? 40 molecules of ammonia is going to get made. All right, so that should really summarize the entire BCA table and hopefully give you a clue to how these two things up on top are going to work. That said, let's go ahead and give you an opportunity to go ahead and try one of these problems yourself. And the way we're going to do that is give you sample problem number 2. So problem number 2 is at the bottom of your page. Let me erase all this stuff. And let me make sure that you see the answers once again. Okay, here we go. So you'll notice that I have the same answer key set up here, but this time I typed it so you can see it. You'll notice that just because I knew it was important, I highlighted the hydrogens 20 because that ended up being the limiting reactant. All right, so let's go ahead and then take a look at example problem number 2. All right, I'm going to give you a moment or two to take a look at sample problem number 2 so you can try it. A sample of 15 moles of aluminum and 20 moles of oxygen are put into a container to react, and you should be able to fill out the BCA table at this point. I'll give you a moment to at least get the before section filled out. All right, as far as the before section, you should have 20 moles of oxygen. And as far as the aluminum, we'll have 15 moles here. All right, take a moment to see if you can fill out what these top sections are going to be. Well, you'll notice that 15 divided by 4 is not a pretty number, but it ends up being 3.75. 20 divided by 3 is also not a pretty number, but it ends up being 6.67, or 666 repeating for that matter. Out of these two, this one is the smallest number. Since that one is the smallest number, see what you can do to fill out the rest of the table. All right, so you've had a moment or two to actually fill out the rest of the table. Let's take a look at the entire set of answers. You'll notice that you have 3.75 ended up being the lower of the two numbers, so you're going to use it to figure everything out. So the 3.75 times 4 gives you a negative 15. The 3.75 times 3 gives you a negative 11.25. And the 3.75 times 2 gives you positive 7.50. And that allows you to fill out the rest of this table. And again, you should be able to answer a whole mess of questions now that you have that. How many moles of aluminum ended up being used up? 15 moles. How many moles of oxygen were used up? 11.25. How many moles of aluminum were left over? 0. How many moles of oxygen were remaining? 8.75. How much aluminum oxide, or the product, was produced? 7.5 moles. So with any luck, these two problems will give you a hand to be able to finish the rest of the packet. If you've got any questions, of course, I am available during the chats. and let me know if I can be of any assistance.